All right, welcome to the 5th STORK summer series. I can't believe we've made it through the whole summer. I think this has been, from my perspective, very successful. We plan on moving into the fall with our STORK fall, maybe winter summer series. So we're looking for speakers to either give a talk on something you're currently doing or running a journal club. So very casual, fun journal club. So if you're interested, please either message me in the chat or get a hold of me somehow. All right, so today we have Aaron Caldwell, and he is currently a postdoc at the U.S. Army Institute of Environmental Medicine. He's going to talk about power analysis, and most of you, I'm sure, know him or of him, and let's just jump right into it. So Aaron, you're up.
Yeah, hi everybody. Thank you for coming. It's great to see a big crowd. This is a topic I'm very passionate about. It's something I started back in my Ph.D. studies. It was a totally ancillary project to my actual dissertation, but I thought it was a pretty important, endeavor to undergo. And it's really, really nice to see so many other people find it important as well, based on the attendance here today. So a little bit about me. I am a postdoc at the United States Army Research Institute of Environmental Medicine within the Thermal and Mountain Medicine Division. So I study human performance in extreme environments. That's what my empirical research is focused on. So the effects of cold, altitude, and heat, as well as hydration on human performance. But I've also developed a kind of pretty strong statistics background. And I think kind of like, marrying those two things together has brought me to this, which I hope these kind of tool sets, and I hope that helps improve your research as well. Let's see the next slide. There we go. Just as a quick disclosure, I do work for the United States Army. Nothing I'm saying today constitutes an endorsement from the Army or the Department of Defense. I have no other disclosures at this time. So a quick refresher as we just jump right back into it. Like, what is power and why is this important? In frequentist statistics, this is what most of us practice. So if you're talking about significance values or significance levels, we're typically talking about the frequentist school of statistics. And in that school, we're concerned with two types of error, type 1 and type 2. So if you want to simplify it, type 1 is referring to false positives, so declaring something is there when it's not. So imagine for COVID, a type 1 error would be someone getting a COVID test, it coming back positive, and then not actually being infected with the virus. And then a type 2 error is a false negative. And so, going back to the COVID scenario, it's someone who is infected, who's tested, and then the test comes back and says they're not infected. Obviously, both of those types of error are important. So when we're designing studies, we actually want to kind of either balance or control, or at least have a certain ratio of the two types of errors. We do this by setting a alpha and beta level. So the alpha level refers to controlling the type 1 error, and the beta level refers to controlling the type 2 error. So statistical power then is 1 minus the beta. And this is a hypothetical probability of detecting an effect of a certain magnitude. So essentially this means, we set up some hypothetical scenario, like we want to be able to detect a, 3 millimeter mercury increase in blood pressure given a variance of 5 millimeters of mercury at a type 1 error level of 5%. So power is essentially, under these conditions, what's the likelihood of us actually detecting an effect? And I think the next question would be, why do we care about these numbers? Now, there's a lot of statisticians who don't care about statistical power. For whatever kind of scenarios they're trying to model, it may not be important to them. But I think for the majority of people that are doing hypothesis testing, if you are using significance testing, it is important, because we want studies to find effects if they do exist. Because otherwise, why do the study at all? Again, assuming you have a hypothesis test. If we are interested in a small effect and collect a small sample size, we are unlikely to detect an effect, at least with a low alpha level. So, maybe you don't go through with a study, maybe you adjust that alpha level up a little bit so you maybe can detect an effect that is there, just with the cost of having a higher false positive rate. And again, I want to remind everybody, there's no such thing as a free lunch in statistics. You know, there's a lot of claims of like, oh, Bayesian analysis, like you don't have to worry about statistical power. Technically, that is true, but it doesn't mean you're going to be more likely to detect an effect accurately with a Bayesian analysis. Bayesian analysis has a lot of advantages. I highly recommend it for a lot of different problems, but you know, you still need to justify your sample size in some way. So a visualization of what power looks like. So if there's no difference, the null hypothesis is true. We're going to have a uniform distribution of p-values. So what I've actually done here is run a simulation with 100,000 tests. Essentially just a t-test sampling from populations where there is no effect, there's a small effect, and there is a fairly large effect. And as you can see here, 5% of those p-values are less than 0.05, right? And so that's your type 1 error rate, or at least what I've set in the simulation, right? And then distribution of p-values with 50%, then 50% of those p-values sampled from that scenario are going to be lower than the significance threshold. And then when there's 80% power, 80% of those p-values are going to be under that threshold. And I think the thing to remember here is, again, under the null hypothesis, p-values are uniformly distributed. They're not, I think a lot of people think it's skewed in the opposite direction where they're more likely to be close to 1. That's not true. They're uniformly distributed with 5% falling under that threshold. And then as you move up in power, either through a larger difference in means or there being a difference in means in a larger sample size, you're going to see that skew in the distribution. More of those p-values are going to start running towards 0. Or skewing towards 0. Slide here. Okay, so traditional power analysis, what does that look like? We try to calculate an effect size of interest. This means we need to calculate a standardized mean difference. So, you know, in the case of, you know, a simple study looking pre-post with some kind of data that's normally distributed, we would calculate Cohen's d, which is simply, you know, the mean difference from pre to post over the standard deviation of the change scores. And that gives us the Cohen's d standardized mean difference. One thing I should note here is this should almost never be used or calculated from a previously observed effect size. Say a previous study had a Cohen's d of like 2. You don't necessarily want to use that for your power analysis, and very rarely want to, because if you're still interested in an effect that's lower than that previous effect size that was observed, then you've essentially set up your study to fail in detecting that effect. All right, the next thing you would need to do is set the alpha and beta / power level, or the balance you want to see between the two of them, and a sample size is then given as the output. So I'm going to quickly give an example of what that looks like in G-Power. So for everybody who's not familiar with G-Power, it's a free bit of software. I think University of Dusseldorf, their stats department or mathematics department has created this, so it's completely free. You can download it online. You can go to this drop-down menu over here. In this case, we're just doing a simple t-test for matched pairs, so pre-post design. We're going to use a one-tailed test because we have a hypothesis that's directional. We want to see if it's going up. It's going to go up by an effect size of, let's say, Cohen's dz of 0.75. Let's calculate. So, you know, the mean over the standard deviation of the change scores gives us 0.75. We want to then have an beta to alpha ratio of 2, let's say, in this scenario, because we find, you know, type 1 errors are twice as costly in this case as type 1 errors are twice as costly as type 2 errors. And let's say we're limited in this case actually to a sample size of 12. All right, so what does this type of analysis do for us? It actually will give us the alpha level we should use in that case in order to balance the two types of error in order to detect this effect, right? And then what we see here is we actually have a power of about 85% in this case with a type 1 error rate of about 0.075 or 7.5%, right? So this is a compromised power analysis in this case. So this is what you would do if you have a fixed sample size. What you could also do then, and what I think most people are used to doing, is an a priori power analysis, which is we just do the exact same thing, but in this case, we put in our desired alpha and beta level. And so let's say in this case, again, we're going back to that 2 times scenario, but we're setting the alpha at 0.05, power at 0.9. And in this case, it tells us the total sample size required in order to maintain that type 2 error rate, and that type 1 error rate is 17, right? And again, that's assuming a one-tailed test and the underlying effect is at least this large, okay? So that's kind of the simple way of doing it. I think the problem is though, and I think the problem a lot of you all have is a lot of your designs aren't simple one comparison pre to post test designs. And then things get a lot more complicated, and the options within G-Power are very limited, especially if you have a between within subjects or all within all repeated measures study design. So let me pop this guy back open again. There we go. Okay, so how do we extend this? Once we extend this, the effect size of interest becomes much less intuitive. For simple pre-post test design, it's the mean over the change score, standard deviation of the change scores. But when you're dealing with an ANOVA level effect, you're then dealing with an effect size called Cohen's F, which is a lot less intuitive. So I like to always ask you, what does a Cohen's F effect of 0.1 mean, right? It doesn't necessarily translate into anything meaningful, I think, for most people in most scenarios. So my partial solution that I came up with in grad school, and a lot of other people have done this or done iterations of this, is to use simulation. And so what I've done is created the Superpower R package and 2 different Shiny web apps that allow you to do simulation in 2 similar, but slightly different depending on your purposes, ways of doing a power analysis. All right. Okay, so how does this work? All you have to do is define a design. So, 2 by 2, all between subjects design. In this case, would be a 2B asterisk 2B. You then set the population parameters. So what you're actually, the population you'd be sampling from. So that would involve the means at each time point or within each category or factor, the standard deviation or variances within each subgroup and factor, and then the covariance or the correlation. And just as a reminder, the correlation is just the covariance over the variance, right? And then from that information, we can, and we also have to assume that there's a multivariate normal distribution. This has assumptions, which is why Superpower right now does not allow for covariance, because the simulation process breaks down. From this, we can essentially run a simulation, assuming this is the population we're sampling from. We can do thousands of samples over and over and over and over and over again. And then what we can calculate, how we calculate power from this, is seeing the number of results that are lower than the set alpha we did in the simulations over the total number of simulations times 100%. And that gives us our power in a percentage form, right? This also allows for simultaneous power calculations. So say you have multiple comparisons, like 8 comparisons, you can do all of them within the same Monte Carlo simulation. So just as a reminder, in this case, I'm talking about a Monte Carlo simulation. Monte Carlo just means I'm resampling from a population over and over and over and over again. And within these analysis, what's very convenient is you can adjust for multiple comparisons. You can actually see what, the effect of using different types of adjustments for multiple comparisons would be, what effect it would have on power or type 1 error rate for that matter, as I'll demonstrate later. So how do we do this? We can use a Shiny web app that I've created. Let's pull it over here. Yep. So that's just at arcstats.io/shiny/ANOVA-power/. It'll just bring you to this wonderful little page here. You can always just look over here, and that's kind of just my little tab where I'll tell you what's new and what's going on with the package. And then I also break down the very basics of how to go through this design, or how to go through this process. So how can we do this? First off, we have to specify our design, as I mentioned. So in this case, we have a 2 between 2 within subjects design, right? And so a kind of example of that in real life would be, we have a treatment and control group in a study, and we measure them pre and post, right? Pretty simple. The package allows you to enter factor names. In this case, I'm not going to do that just to save time. The package also just will will assign factor names and stuff. So it'll give A, B, 1, 2. So A and B being the factors, the between and within, and then 1 and 2 being the level number in those factors. In this case, we're going to set the sample size to 15 per group. And so 15 per cell, that means 15 pre, 15 post in one group, 15 pre, 15 post in the other group. In this case, we're going to set our standard deviation, let's say to 12. Let's use that blood pressure example. And we're also going to, we're not going to enter a specific correlation matrix just to save time, but you can vary the correlations between groups. And let's say the correlation is pretty dang high because our blood pressure measurements are really reliable. And then let's say for the control group, they start at 150. Let's say they go down by about 3, we expect, just because of our selection criteria and regression to the mean. And let's say in our treatment group, we're expecting same at the beginning, and then a drop to about 130. This allows us to set up the design. Perfect. And then what it does is it tells you what your model looks like and what's going to be passed on in the simulation, what this actually looks like in the simulation here. Oh, that didn't work. Hold on. Let me set it up again. There we go. That's what we want to see. So this is what's really important, is sometimes there's little glitches like that. I don't know what causes that exactly, but always check the plot to make sure it actually lines up with what you input into the design. We then see our correlation matrix. Yep, 0.85 within groups, no correlation between. And it also gives it to us in both variance, which is the diagonal, and covariance, which is the off diagonal. Perfect. So that's all set up. We can go ahead and go over to power simulation. You can set a seed, and that essentially means if I set 125 as the seed, let's say, every time I run it, it's going to give me the exact same output, right? So if you want a reproducible analysis, you need to put in a seed number. Sphericity correction, we don't need to worry about that, but that's another assumption. You can violate that assumption and then apply a sphericity correction. So if you are aware, this currently allows you to do a greenhouse gas or a Hume-Felt correction. Let's say in this case, we're not interested in estimated marginal means or exact t-test. We just want to look at that interaction. We're going to set the total number of simulations to 2000's alpha level of 0.05. It's going to run. Oh no. All right. Well, I have broken something here because typically what's actually supposed to happen is a little progress bar is supposed to pop up in the bottom right-hand corner. So we're going to wait here for just a second. And if it doesn't pop up here in a second, then I'm just going to keep going because it's probably just taking a while to process on the server for some reason. All right, 3, 2, 1. Okay, we'll go to the next slide, and I guarantee you it'll probably be up here by the time we get done and do the next slide on here. So the other way of doing this type of power analysis is by using an empirical distribution. And essentially this means instead of setting population parameters and resampling again and again and again from that same population, we just set the sample estimates to match those population estimates. So, say we have 2 groups, we set the mean of 1 to 1, mean of the other to 2, standard deviation of 2. This means it's going to output a data set that has exactly those values with the exact number of subjects as well for those values. We can then perform a power analysis using the effect size estimates from the empirical distribution. So essentially it's a way of simulating post-hoc power. So this is much faster. It runs in like a second, as you'll see in a second. But there's 2 limitations. Complex designs can't have small sample sizes. So if you have a 3 by 3 by 3 design, the minimum sample size right now you'd have to input is 27 per group. And that's just simply because creating that empirical distribution has all of those characteristics that you want. The program can't do that currently. And you can't correct for multiple comparisons. You can't really correct for using any type of sphericity correction. So those are the 2 main disadvantages to using this type, but it is much, much quicker. So let's pop back out of here again. Yep, and as we see here, the simulation, so the Monte Carlo simulation, as you saw there, takes about like 30 seconds or a minute to run about 2,000 iterations or simulations. And as we can see here for this particular study with the alpha set at 0.05, that interaction effect that we saw, which was probably unreasonably large is what I put in there, we would actually have 100% power to detect that interaction under the current parameter settings. All right, and so let's do this exact same thing, but over in ANOVA exact. So this is the one that uses the empirical distribution. Again, let me pop back over here and see what the design I put in. 15 per group. Standard deviation is equal to 12. High correlation. And I should be able to just copy and paste these guys over. Well, it didn't work exactly how I wanted it to, but let's make this a tad more conservative, let's say 140. All right, we set up the design. Perfect, looks exactly right. Design is right, variance, covariance matrix, all looks good. All right, we can then just go through the exact same process again. As you can see, there's less options because with the empirical distribution, we have less options. And so we can run it and see in this case, we reduce the effect size slightly. And you'll see we have 80% power to be able to detect that level of interaction, which is, roughly a, 7 millimeter of mercury difference in the slope between, pre to post in this case. All right. So you can see much faster. One of the other things you can do with this as well is enter in a power curve. So let's say we want to see what the power would be from 12 to 30, and our desired power is 90. So it's actually running, and it'll give you an output and tell you what sample size you would need in order to have 90% power at an alpha level of 0.05, given, again, those parameters that you input. All right, so that's kind of a useful feature. And then what you can do is take these values, take those designs, pass it on to ANOVA Power, and then maybe if you want to put some of those corrections that I mentioned on the data, you can do that. But this just runs a lot quicker, especially if you're going to do many, many iterations. All right, so that's ANOVA Exact. Okay, so there's a lot of other caveats that come with this, and one of the most common questions I get is, hey, Aaron, what do I know what my mean standard deviations or correlations could be? Like, how do I actually enter that? Like, what's an empirical process about determining what's reasonable there? And one of the things I want you all to remember is power is a hypothetical probability, right? So it's the probability of detecting an effect given all of those factors within your design, right? So the best thing I can say is be skeptical and select reasonable parameters. So, don't overestimate the correlation within subjects factors. Maybe take a lower bound estimate from a confidence interval if you have retest reliability data. Look at the studies, look at previous studies of what the variance they're observing for the between subjects variance. And then for the mean response, let your hypothesis drive that, what that should actually look like. And I would also think, what would the most skeptical reviewer think of those parameter estimates or those parameters that you're setting for your simulation? I think, though, that one of the main advantages is the presentation to funding agencies or IRBs will be much more straightforward. Rather than just saying co-and-zef of some number, you can actually, give them a graph that looks like this with the variance covariance matrix and say, yeah, this is the hypothetical design we're going to go do, and yeah, we, with the sample size we have input here, we'll have 80% power to detect that interaction effect, right? So I think it's way more intuitive. It's a much easier way to kind of sell your design to both, IRBs, funding agencies, whoever it may be, that you're having to justify your sample size to. Oop. Not done with that slide yet. And then when you're writing it up, I would say, given these parameters, and you'll say mean, standard deviations, correlations, all the things you entered, we expect to have adequate, whatever percentage power, given the sample size of X per group and an alpha level of whatever the alpha level ends up being, or whatever you've decided to set it to. This way you're presenting your entire design rather than those non-intuitive effect sizes, which those effect sizes are still useful. I'm just saying, it's very hard for me, at least, to kind of get a good heuristic of what those mean for any kind of study. Okay, so now we're going to go into more advanced stuff when it comes to power analysis. So I'm going to do a little bit of code. Nobody freak out. I'm just going to kind of give you a brief introduction, kind of like how I was taught how to develop these things. Biggest thing here is superpower doesn't do anything. It has a limited ability to even do unequal sample sizes per group. We do allow that within the Monte Carlo simulations. I really can't think of a plausible way to do it for the empirical ones. So it'll be a lot slower. No covariate options, but that should probably come within the next year, where at least you'll be able to add one covariate. And then the other big one is we're assuming a multivariate normal distribution is what we're sampling from, and that has that's only one of many distributions. So what can you do if, superpower doesn't fit what you're trying to do? Well, you can code it for yourself. Essentially, all you need to know is how to use for loops and replicate functions. Again, I promise if you understand the basics of R, it's not that difficult to do these things. And again, I actually learned how to do this originally in SAS, and I've seen this done in Python as well. So it can really be done in any statistical programming language. Doesn't have to be a statistical programming language. So as an example for another package, Faux does this as well. It's another simulation package for R. It's very similar in design to Superpower, intended to simulate multi-level designs. So think of designs where you have students nested within schools, nested within school districts, nested within so on and so forth. So you want to account for the variance at all those different levels. So I'm going to quickly kind of go through a little bit of R code, and I'm going to go through it fairly quickly because I want to give a good amount of time for questions here. So just to orientate you towards the basics of simulation. So by the way, this R script will be available online. I'll have the link below the video on YouTube. All you need to do is assign an object that gives you the total number of simulations. So in this case, we want around 1,000 simulations. We then set up a data frame to set up or save the data from our simulations. So the data is set up where we set run to 1 to run. So it's going to have 1,000 rows. And then we give the p-value column just no assignment right now. It's just going to be empty with not available. All right. And then what we do here is we run a for loop. And so essentially it's saying for I, so what iteration, in 1 to runs. And runs is 1,000. So it's going to go and run I 1 to 1,000. Right? So it'll go through. And so the first time it runs, it's going to do I is equal to 1. Second time, I is equal to 2, so on and so forth. What we can do here is we can then sample from a normal distribution with 30, sample size of 30. And then the mean is 0.5 and the standard deviation is 0.75 from that distribution. And then we're going to run a t-test on that data, just a one sample t-test where we're testing if the mean of X is equal to 0. We're going to do a one-tailed test, and then we're going to save the p-value from this. All right. So we set that up and go. Already done, really quick. All right, and then we can see what that data looks like. So what we have here is what level or what number in the runs this was, and then it gives us the p-values from all those. Right. So sometimes they're way lower than our 0.05, the traditional 0.05 threshold, and sometimes from the first 6 here. Size 0.38. All right, and then all we need to do is get the mean of the p-values for which are less than 0.1. Right, so it's essentially just going to count the total number that are less than what the alpha level in this case would be 0.1. And we multiply that by 100. And so in this case, the estimated power for us to detect, a 0.5 difference with a standard deviation of 0.75. With a sample of 30 is about 71, 72%. Okay. You can do the same thing with linear regression. In this case, we may sample, 30 people with a, mean of 10, standard deviation of 1.5. We then can create a slope that has a, 0.8 increase slope with every increase in X. And then we can run, a simple linear model in R and actually get the p-values from that linear model, right? Or in this case, we're specifically getting the p-value for the slope of that line, right? We're just trying to see is the effect of y, equal to 0? And we can run that again. In this case, we're gonna have a much lower alpha, 0.05, because it's a pretty strong effect. I'm gonna load 2 packages, mass and broom. As you can see here, it's a more complicated simulation, so it took a little longer to run. As you can see here, it gives us a mean estimate of 0.8, right? And that makes total sense because that's what we input into the model, right? So the more you sample, the closer it's going to get to the estimate that you put in. And then we have 86% power approximately from those 1,000 runs that we did. And then we can get more complicated with something like Faux, which allows us to specify the level of treatments, the effective time, and that what we can even do then is specify how we're going to analyze the data. So in this case, I'm actually adding in a covariate which we'll think of as like body weight, right? So let's think of, some type of treatment where body weight may be a covariate over the course of some, repeated measures design. And then we're going to analyze it with a simple ANOVA. And I know I'm passing through this a little quickly, but I want to give enough time to kind of give you guys a full exposure to what simulation looks like. And this iter function is then, or iter fo function is then going to run that same analysis that I've run above real quickly over and over and over again for me, right? Or it's going to pass it on to a replicate function that will run it over and over and over again for me. All right, so I'm going to save this function just by going to the end and clicking Control Enter. And then we can actually run this function using PBMC lapply. And I like this function, and I should have really incorporated it into superpower from the beginning because it gives you a progress bar, right? And so as you can see here, again, we're talking about an even more complicated simulation, so it's going to take even more time. And so you can see from this timer down here, it's going to take about 30 seconds to run through this entire simulation. Again, because it's more complicated, I'm requiring more packages. It takes longer to generate the data within each iteration. So it's running. And if you actually are using like a MacBook, you can run multiple cores, which will actually speed up this process. Again, in this simulation, I'm going to set the p-value to 0.025. And as you'll notice here, I'm only returning one value, which is the p-value, this time for the specific comparison I want, which is the 5th row from the model. In this case, we have 96% power, approximately. Again, only going through 1,000 runs, but that should get us at least in the ballpark of what the power looks like. So that is essentially the basics of any type of simulation-based power analysis. You have to have a data generating procedure. So whether it be using the faux package where you specify things and it generates that data. So in this case, it's using sim design, or if you're just using very basic functions like rnorm, which is just sampling from a normal distribution, right? And you just specify the sample size, the mean, standard deviation. Either way works, and then all you need to do is just replicate that process over and over and over again for a large number of times, get the output from those models from that large number of times, and then calculate the number of times it's less than your significance level, and boom, you have at least a estimate of what power would be for your study. Which I know it's pretty complicated, but hopefully you are at least getting a little more comfortable with these ideas. Let's flip this real quick. Okay, so more advanced cases. So let's say, for example, you're not dealing with a normally distributed data. Let's say you're dealing with count data. So I actually do some consulting, and one of the things that we kind of deal with with this consultancy is a problem related to counts. And in this case, they're talking about studies involving diarrhea. So they're counting the number of voids they're having in a day. And so in that case, the Poisson distribution may best describe that data. Although I've read some stuff, negative binomial may be better, but that's neither here nor there. A nice funny XK or whatever that comic is joke about the Poisson distribution. It can't be less than 0, so it disappears. And so what does that look like in R? Well, we can use, scroll down. Yeah, simulate Poisson. It's only Poisson if it includes count data. Otherwise, it's just sparkling Gaussian. We're going to call on 2 new packages, this time SimStudy and EM_means. SimStudy is a great way to simulate study designs because it's so flexible. All we need to do here is create a function that will generate the data definition. And all this does is, I'm going to create 2 variables, age and voids, because in this study, let's say, I have 2 kind of predictors of interest, or an outcome and then a covariate, age being the covariate here, which has a mean of 55, variance of 49, comes from a normal distribution. And then, that's not right, that's an old note. And then we're looking at, the treatment effect, reducing the number of voids by about 3 per day, right? And then we have a data generating function, which essentially just goes through and is adding in all the data and assigning a treatment to the different groups. So we just need to run both of these real quick. And then I'm just going to run through a quick test of the analysis. So it's just going to go through, it's going to use a generalized linear model that has the Poisson family distribution selected rather than Gaussian. Perfect. Model runs just fine. So I know my data generating procedure will work. And then I set up another function that's going to iterate. Essentially, this is the function that's going to go through it. At the end of the day, it's going to put out this p-value from the estimated marginal means. And I'm going to see how often we'll be able to detect this effect given those parameter estimates. And then we can go through this 1,000 times again. Again, it's a little more efficient than the last one because there's probably a little more efficient code here than the faux package had. So it's going to run through, loading, 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 loading. Then we just do the same process we've done with every single one before this. And boom, what we find here is with an alpha of 0.025, we'll have a power of roughly 88%. Assuming this covariate with this relationship and this level of treatment effect. Okay, so again, I know really complicated, but the big important thing here to learn here is that you can sample from different distributions. You can sample different types of data and still do simulations to estimate power, right? Once you learn to code, it gets way more flexible. And I have another, if we want to, I have another advanced case that I can show you all, but I feel like we're kind of hitting a certain limit here as far as what most people are starting to feel overwhelmed. Okay, so some concluding remarks and then we'll get to questions. Simulation is a powerful tool for estimating power. It's not limited to power. So you can also use it for seeing what effect violating the assumptions are. So you have like an assumption like say, homoscedasticity. So assuming the variance in both groups you're comparing, let's say in a t-test, has on the type 1 error rate. So you can actually vary that, say there's no mean effect, and then run the simulation over and over again to see how high your type 1 error rate actually gets. I do this quite often. You can actually do this with superpower as well. Again, it's a great way to set up your analysis pipeline because if you write this code for the data generating procedure, you essentially have your code for when you eventually get your data and analyze it, right? You have your model information, all of that right there. You just need to plug in the new empirical data set that you have. Again, the same thing can be done and should be done actually. Solomon Kurz has done a wonderful set of blog posts on Bayesian power analysis, where essentially you go through the exact same process and, essentially whatever your end marker is that you want to be able to detect, you just put that in as what's being output. You see the number of times within that simulation that you actually get, whether it's the credible intervals width or whatever. And that kind of brings me to my next point, which is you don't even need to use power as your justification. You can use something called accuracy and parameter estimation. And essentially all this means is you're running through the simulation and you can maybe calculate the width of the confidence intervals or measure the standard error and see the number of times within that simulation that the confidence interval width or the standard error is less than a pre-specified value, right? Because you may just want to say like, oh, at this, with these parameters, 80% of the time we'll get a accurate enough confidence interval, right? And that's totally another valid way to estimate your sample size. And then as a concluding remark, don't fear the numbers. I promise you with training and just practice, you can do this. 2017, I think, was when I was introduced to simulations in general while I was in graduate school. And, 3 years later, I've written a pretty extensive package on it. So I promise you, if you invest the time, you'll be able to do this. And it's a great tool to have. So first off, I just want to thank everyone at the United States Army Research Institute of Environmental Medicine, especially all of those who tolerate me babbling about simulation all the time. And special thanks to my mentor there, Nisha Charkoudian. I also want to thank my collaborators who have helped me develop the Superpower R package. Daniel Hawkins, who's my co-author on that, put in a lot of the legwork, both initially and even to this day. Frederick Aust, who's totally responsible for the estimated marginal means portion of the package. and Lisa DeBryan, who really helped us early on solve some of the issues with our variance covariance matrix problems. And then lastly, I want to thank Ronna Turner, who was the professor who introduced me to simulation-based power analysis. Dr. Turner, if you're here, thank you so much. This is such a useful tool, and I'm glad I learned it. So I guess that's all I have as far as initial slides, and we have a little over 15 minutes for questions. So I guess I'll open up the floor for questions. Vanessa, I can't see the chat if you want to.
Oh, you can't see the chat?
Not at the moment.
Okay, so early on, there was a question about what is the seed? So I think that was
great. Yes, so seed just, I don't know where the term actually originates, but seed essentially means when you're running the simulation, it's going to start with the same set of random numbers. So that means if you set a seed, if you went back and reran the simulation, am I muted? Oh, no, okay. Okay, good. It's going to produce the same analysis. So just as an example, I can open up R again. And so we had 0.87 here. I've not set a seed for this simulation. So if I do this exact same thing over again, it's actually going to give me a different value. Yes, and while I had another great question, do you have any good resource to start out with power analysis, R simulations for faculty, grad students who are new to this? Absolutely. I'm going to put a link in the chat right now. I've actually started writing, need to make sure it's the whole group. Perfect. Started writing a book on this. So it's specific, it's specific to the superpower package, but I have links to other resources within there on the cover page of the book. It's all digital, so you can Control F search through it and find what you need. So you'll notice here I didn't set a seed, so the simulation numbers are slightly different. So that's just one thing to remember. If you set the seed, it will replicate the exact same thing. Oh yeah, can I recommend some literature for sample size estimation based on the accuracy approach that I mentioned? I have to say, I've not found a really great introductory resource for that. Again, the process is exactly the same, except instead of outputting the p-value at the end, you would just output the parameter estimate you're interested in, or the standard error of that parameter estimate you're interested in, or no, the confidence interval width for the standard error. And then what you would do here is just count the number of times it's less than that accuracy that you want to see. I think anything, it's not Kelly and Proctor. Let me pull this up. Yeah, Kelly and Maxwell. So anything, literally anything by them. All of these papers are just fantastic resources. I will say though, they're a little intimidating at first to read, and yeah, they're just a little intimidating, but there are packages. I think actually even the MBEST package. So I'll put that in the chat as well. The MBEST package in R allows for some simple parameter estimate, sample size calculations in R. So I think that's limited to simple ANCOVA, some ANOVA designs or factorial type designs, and then any t-test and correlation, it's fully covered.
So there was a question before Robin's. Lena has a question. Can you see that one?
Can you clarify how to use Shiny to estimate sample size? This is a really good point. So this is a very good point. So with the Shiny apps, as was mentioned, like how do you actually go in, set your power and alpha level, and find the sample size required, right, to balance those two? Superpower currently does not do that. That was never the intention, let's say, for the package. It was more to set up a design and then see, with varying alpha levels what your power would be. But we're working on that. So I can actually switch over to my developmental branch of Superpower here. Save these. Again, I'll have a link to this, and hopefully it'll be a little better annotated when I upload it. Right. And so the main problem that I found was, it's not intuitive to enter in like the Cohen's F. But what you actually get from something like ANOVA exact is a Cohen's F value, exactly what it would be given that, standard deviation, means, variance, covariance matrix. What we can actually do then is use that value and then use this new function that I'm created called power Ftest. And it will go back and calculate that for you, what the degrees of freedom would be actually. But what's actually even nice about this function is you can use something called optimal alpha. So it can actually show you what alpha level given the sample size would actually keep your error rates, combined error rates, type 1 and type 2 the lowest. The other function to use is actually plot power. And I apologize in advance. The ability of that section of the package is a little bit limited currently, but I'm working on it. So I'm just going to quickly set up here. Just going to quickly set up a design again in here. Perfect. I'm going to run it. And then I can go down to the power curve tab. And then what it's doing here is the sample size. This is again sample size per group. I think I had, let's say we want to see what power would be between 8 and 100. Desired power would be then entered here. It's going to probably take about 10 or 15 seconds for this to run. And then it'll tell you, like, so within that range, if sample size or the power is never achieved, it'll tell you what the highest power achieved was at what sample size. So for this, in this case, the interaction, you'll get the desired power at an N of 25. Again, it's limited as of now, but I'm working on extending that. So we should be able to go for any sample size for any design, probably here in the next month or so. Stephanie had a question. Is there a way to enter different standard deviations in the design rather than using a common standard deviation? Great question. You cannot do that with the exact simulation, but you can do it for the Monte Carlo simulation. So again, another great resource would be this paper that me and Daniel wrote that kind of details the basics of our package and goes into these. So I'll put that in the chat for everybody as well. So if we go to design here, would you like to enter multiple standard deviations? Warning, this violates the homoscedasticity assumption. So one of the things I would suggest doing here is if you do enter standard deviations is run 2 different simulations. One where there is no effect and one where there is the hypothetical effect, and see what effect varying the standard deviations has on your type 1 error rate. So if I say yes to here, you'll notice that that one box disappeared and the same box that appears for your means now appears for your standard deviations, and they can be entered. All right, another question. Another hypothetical question, how to interpret an underpowered study? Let's say N of 10 subjects per group, and the true effect may be something like D equals 0.4. We get some significant result with 0.8. What to do with this? Be happy with the large effect or be skeptical about reproducibility or something else? So this is an interesting question. If you're interested, if the smallest effect size of interest is, 0.4 or, 0.4 standard deviation increase, like you do want to design your study to detect that effect. But just because, a study that would be underpowered to detect that effect of interest detects an effect, much larger, say of 0.8, which I don't think that would be, I don't know if it would even be powered to detect the effect of 0.8 with only 10 subjects per group. I'm not a big fan of post hoc power, I'll say that much, as far as like looking at a study, seeing if they're underpowered to detect that effect. But there's a little bit of both, I guess. Is in some cases you do need larger studies to detect some of the smaller effects we're looking at. In other cases, one of the ways to also increase statistical power is to reduce the variance. So if you have a highly reliable measure, like me and another statistician were talking about this yesterday, like a measure like ultrasound-based muscle thickness that has like a test-retest correlation of like 0.997 or something like that. So really, it doesn't take a very large sample size to detect those effects, not because the mean differences are large, but because the variance is so small. So I'm not sure what to necessarily do with a study like this. If you only have 10 subjects, I think the right interpretation is you don't have much sample size, or you at least have a very noisy effect size estimate. So the confidence interval around that 0.8 is going to be fairly large. So I think the best you can say is, there may be an effect, but we don't really know how large it is. That would be my interpretation of that study. Yeah. Any other questions?
I have just your comment on you don't like post hoc power.
Yes.
So where does that put people like reviewing papers or can you, I found that interesting. Can you expand on that?
Yeah. Here's the deal. If you have a non-significant p-value, you're underpowered to detect the effect that you found in the study, period. Right? So I think it's a really irrelevant point in many cases, to include those calculations within the paper. Now, where it becomes important is if the study has some interesting comparisons, didn't detect anything, but the estimated differences between groups or relationship between groups, whatever you're statistically trying to measure or estimate, is still something that you as a reviewer find valuable and they didn't detect it. Then the conversation becomes like, well, why didn't you set up your study to detect this effect, right? Why is the sample size so small? Post hoc power is really just a transformation of the p-value that you observed. So I don't necessarily find that useful. I think the debate comes in of whether or not the a priori power analysis or sample size for a given study was actually useful for what they were trying to detect. I would love language in papers to be more along the lines of, in interpreting results, like, yeah, we had a non-significant result, but we can't exclude that the effect isn't at least such and such large, right? And so that gets into a whole other conversation, which is equivalence testing. This whole idea of like the confidence intervals, the upper bound of a confidence interval may include a value that we do find interesting. So we can't exclude that either, just like how we can't exclude 0. It's a little complicated, but I personally just don't find post hoc power to be that helpful.
Thank you. All right, any other questions? I had one more, just for people that are, excuse me, super new to R. Can you put up your environment that you're coding in and just kind of say what it is, just for people that are building their knowledge base?
Yeah, so this is our studio. So it's running R in the background. So this is actually, it's not proprietary. Our studio is free as well. So it's a free language to run. Let me actually pull open a script here. So right now, this is actually the package development environment. But I have some code here that I kind of just have lying around because I like to test my code as I go. And I actually build tests into it as well. So what it essentially has here is you have your code windows. So this is just scripts, or in this case, even a function I have open. Over here, it just tells you a little bit more about your environment. So in this case, the environment's empty, but like say if I ran you call superpower in and then run this line of code here as well, right? Then that will pop up there. So it's actually showing you all the objects that you saved. The console is then where everything can print. So if I were to say, now print for me, design results, and then let's just select design. It'll then print that there. This is actually just showing you, it's just like a file viewer. Your plots will show up here. Packages that you have loaded in R will show up here. It's taking a while to load. There you go. Help. So if you go here and just click in, like say, ANOVA design, it'll actually pull up information about the functions you're using. So I find R super useful, but I'm not a, I'm not strict on what coding language you use. I just prefer to code because it gives you so much more flexibility in your analysis, whether that be SAS, R, Python, Julia, whatever it ends up being. I prefer to do my statistics that way. So yeah, this is just RStudio. It's one of many ways. You can actually even run R in something called Anaconda. So that actually is for Python. So I do a little bit of Python work. I'm trying to.
All right, you have one more question from Andy.
Perfect. Andy, could you go into a little more detail? Hold on, let me say it out loud so you can hear what I'm saying. Could you possibly go into a little more detail on where to select or estimate the correlation of, among within subjects factors input for superpower? You mentioned test retest reliability and variance covariance. Would this be different, I assume, for each variable you measure? Yeah, absolutely. So the first place to start is with like a test retest reliability study, and actually see like for that measure, like what's the covariance, you know, between within that measure over time. Man, Anaconda's taking a while to load up. So you could do it that way. The one caveat to that would be is that sometimes a treatment effect, I'm trying to think of a scenario where this actually occurs. Altitude, let's say. So you have a test retest reliability of like a ICC type 3 of like, you know, 0.9, let's say, for a 5 kilometer or 2 mile time trial. This is something we've done at Arium. That's roughly what we have. When you then measure pre-post correlation for studies involving altitude, that correlation actually goes down, and it's something more like 0.85. And I can tell you for a fact it's lower, right? And that's just because you have actually the effect of the treatment is actually affecting that reliability, right? You know, there may be some, you know, subject by treatment interaction as well. So that would be the one thing I would be careful about when using test retest reliability statistics for that within subject correlation, is that sometimes they may be overestimates for a given study that involves some type of treatment, because the treatment itself may affect that correlation. So you may want to look at previous data, maybe a meta-analysis, to get a better idea of what that correlation looks like. Hope that helps. It's not easy, for sure.
All right, we're at the top of the hour. So thank you so much, Aaron. I think you have expanded everyone's knowledge wherever they came into this session. Again, we're looking for people to present going into the fall, so please let us know. And then everybody have a great day.
Yeah, thanks everybody, and feel free to reach out. I'm on Twitter, Ftest student, if you have any questions or lingering concerns.
All right, thanks everyone.